Okay, so today we are very happy to have Tristan Collins from MIT to talk about Is Syz mirror symmetry for their Pezzo surfaces. Let's welcome.
Thanks very much, and thanks for the invitation to speak. It's an honor to speak in this festival. So I'm going to talk about something which is sort of between Calabi-Yau geometry, Syz sort of mirror symmetry, and maybe classical algebraic geometry. So let me begin by I'll first sort of introduce the main players in this story, which are low-dimensional algebraic varieties, and then I'll talk a little bit about mirror symmetry and how it applies in this particular setting. And then I'll talk about some of the aspects of Syz mirror symmetry that I work in this for Del Pezzo on the Del Pezzo side. And then I'll talk about some of the aspects of Syz that live on the rational elliptic side. And then how these two fit together to give a sort of duality between these two sort of classical objects in algebraic geometry. Okay, so Del Pezzo surfaces. So a Del Pezzo surface is a projective surface, so complex dimension 2, which has an ample anti-canonical bundle. So there's not very many of these. They're all classified. They're either P1 cross P1, or you just take P2 and blow it up between 0 and less than 9 times generic points. And they're essentially classified by their degree, which is 9 minus the number of times you blew up, except for in the, well, okay, so for degree not equal to 8, they're classified by this construction up to deformation, so there's only really one family. And in degree 8, there's 2 families, which are the blow up of P2 and a point and P1 cross P1. So very sort of simple, relatively simple classical objects. They all have, just a technical point which I'll just mention right now, is that they all have smooth anti-canonical divisors. So there's some smooth divisor that is a 0 section of a anti-canonical section. So rational elliptic surfaces, these are maybe slightly less well known. So these are complex surfaces, again, so complex dimension 2, compact. They admit a relatively minimal elliptic fibration onto P1, which has a global holomorphic section. So maybe more concretely, the way that you can get a rational elliptic surface is you take 2 cubics in P2. So if you take 2 generic cubics in P2, they'll intersect at 9 points. You just blow up those 9 points, and that will give you a rational elliptic surface. For these guys, the anti-canonical bundle is effective. It's not ample anymore, and each fiber of this map to P1 will be an element of this anti-canonical linear system. So there are lots of smooth fibers, and they're all tori. And then there are of course singular fibers. And these are all classified by Kodaira. So there's going to be a special type of singular fiber that will play a role in this talk, which is a singular fiber of type IK. So I'll draw a picture in a second, but these are just what happens when you take a torus and you pinch off, let me think, KS1 cycles. So you end up with a bunch of nodal spheres connecting at their endpoints. So let me draw a quick picture just to put this all into context. So, so rational elliptic surface is some surface. Here's Y, rational elliptic surface, has a map to P1, whose generic fiber is a torus. There's a torus. I have to forgive my bad drawing. So an IK fiber looks, an IK singular fiber is something that looks sort of schematically like this. So I guess this would be 1, 2, 3, 4, 5. This would be an I5 fiber. So each of these is a -2 curve. And this is what happens when you pinch off 1, 2, 3, 4, 5 S1s. So this would pinch off to some sort of collection of nodal spheres, something like this. So these are all S2s now in this picture. Okay, so this is a kind of thing that can happen. This is a very common type of singularity to see in these elliptic fibrations, rational elliptic surfaces. Okay, so these are the two main objects or main sort of characters that are going to appear in this talk. So in either case, if you take a del Pezzo surface or a rational elliptic surface and you take one of these anti-canonical divisors, then since it's the zero of some anti-canonical section, you can invert that anti-canonical section and you get a holomorphic 2-0 form, which has a simple pole on the divisor that you've chosen. So in particular, you can think of the complement of that divisor. So if you just throw that divisor away, you can think of the complement as a non-compact Calabi-Yau manifold or surface in this case. So this is sort of just a purely holomorphic compact Calabi-Yau. It's important to note that Ricci flat Kähler metrics don't necessarily exist, or at least their existence doesn't follow from Yau's theorem, since the manifold is non-compact. So let me say a few things about mirror symmetry. So mirror symmetry was originally discovered in string theory as a sort of mysterious duality between different Calabi-Yau manifolds. An essential feature of this duality is that it's supposed to relate complex geometry of one Calabi-Yau to symplectic geometry on its mirror dual pair. So for example, so a sort of instantiation of this principle is that if you look at the moduli space of complex structures on one Calabi-Yau manifold, then that should be related to the symplectic moduli of the Calabi-Yau structures on its mirror dual. So for example, on the complex side, we know that the moduli space of complex structures is determined by this Hn-1,1 cohomology group. And of course, the symplectic moduli is determined by the 1,1 cohomology group. So this is this sort of interchange of Hodge numbers that one sees for Calabi-Yau for mirror pairs. Okay, so, and this is just a particular case of what became, so the sort of reason it's called mirror symmetry is you get this sort of symmetry between the Hodge diamonds of X and its mirror dual. Okay, so now at this point, you know, mirror symmetry has been around for a while. There are several different ways to interpret mirror symmetry, and they live at sort of different levels of detail. So there's Hodge theoretic mirror symmetry, which asks to just construct pairs of Calabi-Yau manifolds with mirror symmetric Hodge diamonds. So that's maybe, you could think of that as some sort of topological mirror symmetry. There's homological mirror symmetry, which was proposed by Kontsevich, which says that you should construct the way to interpret mirror pairs is that they should have their derived categories, the sort of holomorphic derived category, which is the derived category of coherent sheaves, should be equal to the symplectic derived category, which is this derived Hyperkale category of the mirror pair. And then there's a proposal of Strominger-Yau-Zaslow, which suggests how we should try to construct mirror symmetric pairs, and it also makes a lot of predictions about the metric geometry of Calabi-Yau manifolds. So let me explain well, I'll come back to this SYZ. So then there's also some recent programs of Gross-Siebert and Kontsevich-Sogelman, which are trying to sort of make this SYZ philosophy work, but in a more combinatorial algebraic framework. Okay, so let me try to explain the picture for SYZ mirror symmetry. So let me recall this definition of Harvey and Lawson. So if you have a Calabi-Yau manifold and it has this holomorphic volume form omega, then a possibly immersed submanifold is said to be special Lagrangian if it's Lagrangian, so it annihilates the symplectic form, and it's calibrated by this holomorphic volume form. So in other words, up to possibly rotating the complex volume form by a fixed unit complex number, the imaginary part becomes 0. So these were originally introduced because they are calibrated and hence automatically volume minimizing in their homology class. That was the sort of original interest. But it's important to note that notion makes sense for omega, which is not the Calabi-Yau symplectic volume form, but in that case, they're no longer volume minimizing. Okay, so what is SYZ mirror symmetry? So SYZ predicts that sort of near sufficiently degenerate complex structure, so near some sort of large complex structure limit, a Calabi-Yau manifold should admit a special Lagrangian fibration, torus fibration, onto a base B. And this base B, so by work of Hitchin, this base B inherits two different affine structures from this fibration, so a complex affine structure and a symplectic affine structure. So then the SYZ conjecture says that you should be able to construct the mirror pair by taking each torus and replacing it by its dual torus. And then that's supposed to compactify to another compact Calabi-Yau or just another Calabi-Yau manifold. And so this mirror dual also has a special Lagrangian fibration onto the same base, in particular from the construction. And this T dual, one way to think about what T duality is that it's supposed to be the operation which exchanges the complex and symplectic affine structures on this base B. Okay, so this is the sort of recipe the SYZ conjecture suggests for constructing mirror pairs. It also makes a lot of, it makes a lot of predictions about the geometry of these Calabi-Yau manifolds near these large complex structure limits. So mirror symmetry beyond compact Calabi-Yau. So if Y is not a compact Calabi-Yau manifold, then there's still a notion of mirror symmetry. But in that case, the mirror is not going to be a Calabi-Yau manifold anymore. It's supposed to be a Landau-Ginzburg model, which is a non-compact Kähler manifold together equipped with a holomorphic function valued in C. So in general, if Y is a compact Kähler manifold and it has some anti-canonical divisor, then Aru laid out a general picture for constructing the mirror to Y by applying SYZ mirror symmetry to the non-compact Calabi-Yau manifold you get by removing D. So Aru suggested that this SYZ philosophy should really work even for compact Kähler manifolds with anti-canonical divisors. So a lot of what I'm going to talk about today is essentially motivated by this picture of Aru. Okay, so what am I going to talk about? So I want to talk about mirror symmetry for del Pezzo surfaces and rational elliptic surfaces, and this is has been studied at the algebraic and homological levels. So, for example, Aru, Kutsarkov, Orlov, they proved one direction of Koncevich's homological mirror symmetry conjecture by showing that coherent sheaves on a del Pezzo surfaces, the category of coherent sheaves on a del Pezzo surface could be related to the Fukaya-Seidel category on a rational elliptic surface. This was recently generalized by Hacking and Keating. Gross, Hacking, Kiel constructed synthetic mirrors along the lines of the Gross-Siebert program. So they sort of enacted this Gross-Siebert program in this setting to construct sort of algebraic mirrors. And then there's a version of Hodge theoretic mirror symmetry in this setting also, which was proved by Luntz and Przyjalkowski. But here, of course, one needs to be careful because the Hodge numbers don't make sense because you're talking about a non-compact manifold. So you need to have the right notion of Hodge number, and that was followed a proposal of Kutsarkov, Koncevic, Pantev. So that's what's, and that, I guess there was also work of Dorn and Thompson who studied a version of lattice theoretic mirror symmetry also. So what I want to explain in this talk is a proof of essentially the strongest form of SYZ mirror symmetry that you could hope for del Pezzo surfaces and rational elliptic surfaces. And then explain how you can deduce a sort of geometric version of this mirror symmetry for Hodge numbers in terms of the sort of classical picture of complex moduli of Calabi-Yau metrics, and then a few sort of applications to some geometric questions along the way, which just sort of happened to come up. Okay, so if I want to talk about classical SYZ mirror symmetry in this non-compact case, the first thing I need to say is what the Calabi-Yau metrics are. So the Calabi-Yau metrics on the Del Pezzo side were produced by Tian and Yau in the 80s. So if you have a Del Pezzo surface with a smooth elliptic curve, so anti-canonical divisor is an elliptic curve. So that's a Calabi-Yau curve. So now you have this holomorphic volume form with a simple pole on D. Then the Tian-Yau theorem says that you can find, in fact, a DD bar exact Calabi-Yau metric on the complement of D, which satisfies this the Monge-Ampere equation. So, and this solution of the Monge-Ampere equation is asymptotic to a model called the Calabi model, which I'll explain in a second. And that's sort of the idea of the Tian-Yau proof, is you have a sort of model solution to your equation near infinity, and then you solve the Monge-Ampere equation in the interior of your manifold. And this Tian-Yau theorem is really much more general than how I've stated it here. It holds in all dimensions, appropriate modifications. So let me explain this Calabi model, since it'll be a little bit important. So if you have an elliptic curve with an ample line bundle over this elliptic curve, so you should think of this ample line bundle as being essentially the normal bundle to this divisor, maybe the co-normal bundle. So you take a Hermitian metric on this bundle so that the curvature is a flat Kähler metric. And now you look at just the unit disk bundle in the total space of this holomorphic vector bundle or holomorphic line bundle, and you can put on this unit disk bundle a holomorphic volume form with a simple pole on the zero section and a Calabi-Yau metric. So this is a Calabi-Yau metric on this unit disk bundle, which is complete at the zero section, but of course not complete when you go towards one. That's supposed to be the interior of the manifold. Okay, so so the way to view the Riemannian geometry of this picture is by considering these circles in this disk bundle. So these are S1 bundles over D, which fiber this or sort of foliate the total space of this Calabi model. And what happens, you can just write out what the metric is. What happens is that as you shrink these circle bundles, these circle fibers collapse, but the base is expanding. So the D in this metric geometry is expanding in such a way that these circle bundles always have fixed volume. And it's not hard to see from this picture that if you take a special Lagrangian in this elliptic curve, which is just a geodesic now with respect to the flat metric, then if you just look at, so in other words, a straight line. So if you look at the preimage of this straight line in this circle bundle, then that's actually topologically L cross S1, and it's a special Lagrangian with the same volume as the thing downstairs, or they all have the same volume, which is essentially the same as the volume downstairs. Okay, so let me draw the picture just so we are on the same page. So what happens, you have to imagine you have D here. So this is this elliptic curve. And now you have these circle bundles, which look like they are. So here's a circle bundle. This is an S1. Oops, S1 inside of this C epsilon, inside of C. And now as you shrink epsilon, what happens is you get these smaller and smaller circle bundles, but they expand in the base direction. And of course, as you take epsilon to zero, the diameter of these sets diverges. So they get longer and longer, something like this. And now what happens is if you take, let me draw geodesic, and my divisor is in this torus as a point. And now you just look at the preimage of this in these circle bundles, and these are special Lagrangian, and they're going to be tori for the most part if you choose a closed geodesic. So these will be So this pink guy here, this is supposed to be a geodesic S1, geodesic circle in the flat torus D. And then this is topologically a torus. So this is going to be S1 cross S1. Okay, use a different color. This is S1 cross S1 inside of this Calabi model, and it's special Lagrangian. So it's so you see that if you take a sort of appropriately chosen S1, then you can translate that around in this divisor in this flat torus D, right? Because D is just C model lattice. And so there's actually a special Lagrangian fibration here of this Calabi model at infinity. So that's a sort of important observation. Okay, so that's the geometry of these Calabi-Yau metrics on del Pezzo surfaces near infinity. So using this picture in joint work with Yushin Lin and Adam Jacob, we proved that that actually you could construct a special Lagrangian fibration on the complement of a smooth elliptic curve in a del Pezzo surface. And so you can construct a special Lagrangian through every point, and the fibration that you get is a fibration onto R2. So in fact, you get countably many distinct special Lagrangian fibrations. So these del Pezzo surfaces, in fact, have a huge number of special Lagrangian fibrations. And the only data that you need is to choose this closed loop in the torus at infinity. So any closed loop you choose will give you a special Lagrangian fibration, torus fibration. So let me just explain how the proof goes. I'm just going to explain the sort of idea. So you fix this curve at infinity in the divisor at infinity, and then by translating it and taking circle bundles over that gives you a special Lagrangian fibration of this model geometry that lives at infinity. And now, because you know that this Tian-Yau metric decays towards this model geometry, you get, by sort of transplanting a sort of almost special Lagrangian fibration of this Tian-Yau manifold outside a huge compact set. And now the idea is you run the Lagrangian mean curvature flow and you prove that it converges smoothly it flows this model fibration to an actual fibration in a neighborhood of infinity. So that produces a special Lagrangian. That shows that you can sort of do this deformation theory from this sort of approximately special Lagrangian fibration to a genuinely special Lagrangian fibration outside a huge compact set. And now the problem becomes a problem of extending this fibration into the interior of the manifold. So to do this, you can use this Hyperkale rotation trick, which says that it's special to dimension 2. You can change the complex structure. So your special Lagrangian fibration now becomes a holomorphic torus fibration. So get some extra rigidity. And then you can use J holomorphic curve theory. So you can argue that these holomorphic curves deform a little bit and that they sweep out a local fibration in a neighborhood of any smooth curve. And then the only problem is to show that you don't get too many singular holomorphic curves appearing as limits of this deformation process. So that takes a bit of work, but it can be done. So that's the idea. You use Lagrangian mean curvature flow to produce a fibration near infinity, and then you use J holomorphic curve theory to extend it into the interior of the manifold. Okay, so there's a natural question, which is that we started with a del Pezzo surface, we produced a special Lagrangian fibration, and then by this Hyperkale rotation trick, we said that that becomes a holomorphic fibration. It's natural to ask what that fibration is. And so the theorem is that that special Lagrangian fibration is actually a Hyperkale rotation from a holomorphic torus fibration obtained from a rational elliptic surface with an IK singular fiber. So K here is the degree of the del Pezzo surface. So in other words, you take this special Lagrangian fibration, you change the complex structure so it's holomorphic, and then we prove that that can be compactified by adding an IK fiber at infinity to give you a rational elliptic surface with an IK fiber.
So the mirror and even though you've done a hyper-Kähler rotation, the mirror is ultimately not diffeomorphic to the original manifold. Is that correct?
So yeah, so I guess it's if you remove the two divisors at infinity, then they're sort of identified pointwise by this trick. But you're right, they're not even, I guess, topologically the same. Yeah. Yeah, if you add the things at infinity, then they're not even topologically the same. Okay, so but I will not claim that this is the mirror just yet. So a question that Yau asked in the 80s, he communicated to us, was that he wanted to know what the symplectic structure of this hyper-Kähler rotation was, because you had this Calabi-Yau metric, you change the complex structure, it gives you some Kähler structure on this non-compact manifold. And he wanted to understand what the symplectic structure was. Okay, so I'll come back to that question in a bit. So now I've explained somehow half the picture of Syz Mir symmetry for the case of del Pezzo surfaces. So now I'll move to the rational elliptic surface side. So we want to prove a similar, sort of show the similar story holds on these rational elliptic surfaces with an IK fiber. The first thing I need to do is to discuss the existence of Calabi-Yau metrics. So in the same way as the Tian-Yau theorem, the idea is to first construct a model for what this Calabi-Yau geometry should look like near the singular fiber that you're going to remove. So the local geometry near an IK fiber looks morally like a holomorphic torus fibration over a disk. And then the fact that you have an IK fiber tells you what the monodromy of this holomorphic fibration should look like. So it looks like just a punctured disk cross C model lattice, and the lattice is Z plus this factor times log Z times Z. So that gives you a holomorphically varying lattice over the disk. And it has some holomorphic volume form with a simple pole on the zero fiber, which is the zero. This fibration can be compactified to give you an IK fiber over zero. So let me just assume that this kappa of Z here, some holomorphic function. Let me just assume that it's 1 for simplicity, some non-vanishing holomorphic function in general. So so the idea is that if you have any IK fiber, then if you choose a section of this fibration, a local section of this fibration, then you can identify your fibration with this model fibration by just using this sort of fiber-wise Abel-Jacobi map. So in this case, Green, Shapir, Vapa, Yau wrote down a Calabi-Yau metric on this model space, which is flat along the fibers. So you can imagine you have this torus fibration, it's natural to try to write down a Calabi-Yau metric, which is just the flat metric on the torus fibers, and then you have to play around with what happens in the base directions to get an actual Calabi-Yau metric. So it has a fairly complicated expression. This is not so important. I just wanted to write it down for completeness. The important thing is to note that it lives on let me go back. It lives on this model fibration. And the way that you get a metric on your actual elliptic fibration is by identifying the two using a choice of section. So you can pull back this model metric using your fiber-wise Abel-Jacobi map. And that gives you a complete Ricci flat metric near this IK fiber. But it's sort of important to emphasize here that it depends on the choice of this section sigma. So let me draw a picture maybe again. So you have some holomorphic torus fibration over a disk with an IK fiber over 0. And then you have this model fibration. Color, red. It's the model fibration, which is just C. This is C mod, this lattice lambda of Z. So now if I choose any section of this fibration, some section sigma, then I get an identification F sigma from this space to this model space. And so I can pull back any geometric information I can write down on the model back to my actual elliptic fibration. So that's the sort of idea, is to use this model space together with the choice of section to induce geometry on the actual elliptic fibration. So the only sort of reason that it's important to write this model down is to note that if you just take these curves, which are given by the imaginary part of the complex variable and the fiber being a constant, then that's actually a special Lagrangian in this model geometry, and hence it's also a special Lagrangian in the actual fibration. So you have a fibration given by these S1s over each S1 and over a circle in the base. All right. So there's also a special Lagrangian fibration of this model geometry, which is somehow the starting point. Okay, so regarding Calabi-Yau metrics, so there's a theorem of Heinz, so Heinz thesis, which says that if you have one of these rational elliptic surfaces with an IK fiber, then you take any, so this special Lagrangian cycle defines a homology class, which I'll call the bad cycle. Well, Heinz calls the bad cycle. Now, if you take any Kähler metric on the complement of this IK fiber, which pairs to 0 with this bad cycle and has finite volume, then you can produce you can find a section and some parameter alpha naught such that there is a Calabi-Yau metric in the Bott-Chern cohomology class of your Kähler metric converging exponentially fast to this rescaled semi-flat metric with respect to this section sigma. So there's a lot of so this constructs non-compact Calabi-Yau metrics, or complete Calabi-Yau metrics on this non-compact manifold. But there's a lot of data that goes into this construction, which is, so you see that there's some statement about the existence of a section and some parameter alpha naught. Okay, so let me just highlight these things here. So there are 3 assumptions, essentially, which is that you pair to 0 with a bad cycle, your Kähler metric has a finite volume, and then you conclude that there exists some section. So the problem, so this produces the Calabi-Yau metrics that we want, but the problem is that if you want to understand mere symmetry, so you want to understand these moduli space of complex structures versus the moduli space, the sort of Kähler or symplectic moduli, then you have to have some parameter space which parameterizes your Calabi-Yau metrics. And the problem is that with the statement of this theorem as it stands is just that there's too many pieces of data here which we don't quite understand how they enter the construction. So for example, the existence of this background metric with finite volume, it's not clear how that influences the construction. And then the fact that there exists some section is also sort of hard to control from the point of view of constructing a parameter space.
Is the K in the IK fiber determined by the degree of the mirror del Pezzo?
That's right. Yeah, they should be. Yeah, they're the same. Yeah.
Good.
Okay, so the outstanding questions then are, well, first of all, the de Rham cohomology. So you can compute if you remove this divisor from a rational elliptic surface, then the de Rham cohomology is 11 minus k dimensional. But this condition that you pair to 0 with the bad cycle cuts out a 10 minus k dimensional hyperplane. So it's natural to ask whether there are Calabi-Yau metrics in the remaining de Rham classes. Secondly, if you want to understand the parameter space or the moduli, Heinz theorem constructs a Calabi-Yau metric in each Bott-Chern cohomology class. And spot churn is a refinement of de Rham. But Hein's theorem depends on a construction which leaves open the possibility of infinitely many distinct Calabi-Yau metrics, even in a fixed spot churn cohomology class. And further, you can just compute what the bot churn cohomology class is. Bot churn cohomology is. It's just the de Rham cohomology across the space of holomorphic functions on C. So it's like wildly infinite dimensional. So it's not really a suitable parameter space from the point of view of mirror symmetry. For example, if you try to define a Hodge number in terms of the moduli here, you would not get a very interesting answer. So in particular, one needs a sort of uniqueness theorem, which is better than just uniqueness within the bot churn cohomology class, because if you want to have a well-defined moduli sphere, you want to have some sort of well-behaved moduli space, you need to be able to cut out these infinite dimensional bot churn contribution. So this already shows that Hodge numbers in the sense of bot churn cohomology are not well defined, which was expected since it's a non-compact manifold. So this Kontsevich-Pantev proposal was to define Hodge numbers in terms of purely algebraic data. So they used various things, sheaves of logarithmic forms, weight filtrations, perverse sheaves, etc. And Lentz and Przylkowski computed these Hodge numbers for del Pezzo surfaces of degree K and rational elliptic surfaces, and they found that the dimension of, or the sort of these Hodge numbers were 10 minus K on both sides, proving this mirror symmetry at the level of KKP Hodge numbers. So one thing I would like to explain in this talk is how to define these Hodge numbers purely geometrically. So I have to do a brief digression on sections of this elliptic fibration. So a section of this model fibration is just a multi-valued holomorphic function. So H here is just some holomorphic function on the disk. And then you have these two extra parameters that you get to play with, A and B. So if you consider the case where this parameter 2b over k is in Q and A plus B is in Q, then what you get are multi-valued sections. So they may take several values, but they're sort of periodic. They come back to themselves eventually if you go around the circle enough times. And if you take R, then actually they're infinitely many valued. They never close up. So one key point is that if you take this semi-flat metric, then actually it turns out that if you pull back by the Abel-Jacobi map with respect to a multi-valued section, even infinitely many valued, then it still yields a well-defined semi-flat Calabi-Yau metric. So there's somehow these contributions cancel in the metric. So we'll call these non-standard semi-flat metrics and say that they're quasi-regular in the case of a Q-valued section, and irregular in the case of an R-valued section. So by Q-valued, I mean sort of finitely many valued over the disk, or infinitely many valued over the disk in the irregular case. So in this case, even for quasi-regular cases, for quasi-regular semi-flat metrics, there's still special Lagrangian bad cycles, but they don't cover a circle in the base once, they'll cover it many times. So you have some sort of torus that wraps around many times before it comes back to itself. So they project to a non-simple loop in the base. And these irregular semi-flat metrics, in fact, cannot admit special Lagrangian fibrations because of just purely homological obstructions. So the theorem that we proved, this is a sort of follow-up paper with Adam, Jacob, and Yushin Lin, is that if you have any rational elliptic surface with an IK fiber and any Kähler metric on X minus on Y minus D, then you can find a multi-valued section such that there exists a unique Calabi-Yau metric in the bot churn cohomology class, converging exponentially fast to this model. So the existence part is just, so Hein has a very robust package for producing these Calabi-Yau metrics once you identify the models. And so once we sort of realize that these you could construct these non-standard semi-flat metrics, you could pretty much just plug it into Hein's paper. The uniqueness part is new, and it follows from a nearly optimal uniqueness theorem, which I'll discuss again a little bit below. And in particular, it shows that the parameter space for Calabi-Yau metrics asymptotic to semi-flat metrics is the cone of Kähler metrics in this Bott-Chern cohomology. So at least we have uniqueness in a given Bott-Chern cohomology class, which is still infinite dimensional, but at least it's slightly more manageable. So, and for various reasons, it turns out that these quasi-regular metrics are actually important for mirror symmetry. I probably won't get into it at the moment. So this actually allows us to answer this question of Yau that I mentioned before. So if you take a Del Pezzo surface and any closed loop in this elliptic curve at infinity, and then you produce this special Lagrangian fibration and Hyperkale rotate so that it becomes holomorphic, then we can identify the symplectic structure. So the symplectic structure is exactly one of these non-standard. Well, it's exactly one of these Calabi-Yau metrics asymptotic to a semi-flat metric. And in fact, it's essentially always non-standard unless you have the case where this divisor at infinity is the torus with a square fundamental domain. And in fact, generically, they're even irregular. And that was somehow how we found these. Well, one of the reasons we thought that we should look for these non-standard semi-flat metrics. Okay, so let me mention this uniqueness result. So the uniqueness theorem says that if you have a rational elliptic surface with an IK fiber and two Calabi-Yau metrics solving the same modular pair equation, and in the same de Rham cohomology class, then provided you assume that they converge to some semi-flat metrics at infinity, then you can prove that there exists a fiber-preserving map, which is homotopic to the identity, which pulls one back to the other. So this says, in a sense, this says that the Calabi-Yau metrics in a fixed de Rham class are unique modulo the connected component of the automorphism group. So in particular, if you take the point of view that the moduli space of Calabi-Yau metrics should be Calabi-Yau metrics modulo the action of the automorphism group, then you see that the moduli space of Calabi-Yau metrics is now just the de Rham, the cone of Kähler metrics in the de Rham cohomology, which is 11 minus k dimensional. So now we've cut everything down to a finite dimensional moduli space. So in particular, this tells us that we can define Hodge numbers in terms of moduli of Calabi-Yau metrics, which is the upshot. Okay, so special Lagrangian fibrations. So with this sort of discussion of Calabi-Yau metrics out of the way, we can turn to this SYZ picture. And so the theorem is that that the same thing that we applied in the case of Del Pezzo surfaces works here. So if you take any single one of these Calabi-Yau metrics on the rational elliptic surface, remove an IK fiber, which is asymptotic to any of these semi-flat metrics, which is not topologically obstructed from having a special Lagrangian fibration, then you can produce a special Lagrangian fibration whose base is R2. And you can, again, Hyperkale rotate and compactify to get another rational elliptic surface. So there's some sort of way of changing rational elliptic surfaces by these SYZ fibrations, moving around in the moduli of rational elliptic surfaces with an IK fiber. Okay, and the argument is exactly the same. Once we have this model geometry at infinity and you have this special Lagrangian model, special Lagrangian fibration, then you can do this mean curvature flow and J holomorphic curve argument. Okay, so now I can discuss mirror symmetry. So using these sort of two packages of results on the Del Pezzo side and the rational elliptic surface side, we can prove SYZ mirror symmetry. So the first step is you find a special Lagrangian fibration on a Del Pezzo with a choice of an elliptic curve. So that was the fibration theorem for Del Pezzo surfaces. Then you construct the topological mirror. So the idea is once you have this SYZ fibration, you can Hyperkale rotate. That gives you a rational elliptic surface, which lives in the right topological family. So that gives you at least a topological mirror. So that at the moment, the complex structure is not going to be the mirror complex structure, but at least topologically, it's the right mirror. So this is a hyper-Kähler rotation. And now the problem becomes identifying the correct complex structure on this complement of an IK fiber in a rational elliptic surface. And that you can use a Torelli theorem of Grossack and Kiel. So you have to think a bit about how to do this, but there's a sort of distinguished complex structure which on this pair, which is this sort of right mirror complex structure. And then you can construct a special Lagrangian fibration on this Y check D check using this fibration theorem for rational elliptic surfaces. And if you construct it correctly, then you can show that mirror symmetry exchanges the complex and symplectic affine structures on R2 obtained from these two special Lagrangian fibrations. So so this shows that really the most optimistic version of SYZ works in this setting. So that's just purely a calculation. So now we can try to compare Hodge numbers. So the Kähler classes on a rational elliptic surface, which pair to 0 with some quasi-bad cycle, that is a 10 minus k dimensional moduli space. So it's a little bit complicated. Let me draw the picture because it's kind of interesting. So you have this, you have the Duram H11, H2 Duram of X. So here X is a rational elliptic surface minus an IK fiber. And this is 11 minus k dimensional. Okay, so let me draw it like this. So here's this H2 Duram. And now if you look at the Kähler classes which pair to 0 with some quasi-bad cycle, so this is the bad cycle pulled back by a possibly multi-valued section, then this is a collection of 10 minus k dimensional hyperplanes, which are actually parameterized by Q. So there's a huge number of hyperplanes here, which is 10 minus k dimensional. These are all R10 minus k. And they're parameterized by Q. These hyperplanes are parameterized by the rational numbers. And so this is the moduli space of Calabi-Yau metrics, which are obtained from mirror symmetry. So every Kähler class here admits some Calabi-Yau metric, but from a mirror symmetry point of view, the only ones that you obtain are living on these rational hyperplanes. So you have this Kähler moduli, which is 10 minus k dimensional. And that turns out to be exactly the same as the complex moduli of del Pezzo pairs of degree k, where you take a del Pezzo surface of degree k and you consider the pair consisting of that and the anti-canonical divisor. So you have this, so this gives a sort of equality of dimensions of the moduli space. Interpret it, so if you interpret the Hodge numbers as the dimension of the moduli space, then we have proved sort of Hodge theoretic mirror symmetry as well. And it's important, it's also sort of interesting to note that these Hodge numbers that we compute are exactly the same as the ones that were computed by Lentz and Przyjalkowski following this KKP proposal. So everything sort of agrees, which is kind of encouraging. What seems harder is to go the other way. So to compare the complex moduli on a rational elliptic surface with the Kähler moduli on a del Pezzo surface. Because at the moment we only have 0-dimensional moduli on the del Pezzo surfaces. So there's sort of no topological moduli or symplectic moduli for Tian-Yau metrics, since they're DD bar exact and we don't know of any other examples. But in lots of examples, these rational elliptic surfaces actually have non-trivial complex moduli. So if you believe that mirror symmetry should also go in the other direction, then that suggests that maybe there's some sort of exotic, not exact Calabi-Yau metrics on certain del Pezzo surfaces for certain degrees. So that's a sort of interesting question for future work. So I think I will stop there. Thanks.
Does anyone have questions?
I have a question. So you mentioned that you use the theory of J holomorphic curves. Can you slightly explain this?
Sure. Yep. Yeah. So the idea. Okay. So let me draw the picture. So you have this non-compact Calabi-Yau manifold X, and we know that we have a holomorphic torus fibration outside of some compact set. So these tori deform they sweep out anytime you have a smooth fiber, it sweeps out a local fibration. I mean, that's essentially because you're in the Hyperkale case, and we know the deformation theory for special Lagrangians. So any smooth fiber sweeps out a local fibration. Sweeps a local fibration. So now what you want to do is show that you can find so if you take a sort of generic point in the interior of the manifolds, take some point here, generic. You want to show that you can find a special or a holomorphic torus through this point. So the idea is that you start, you choose sort of a generic path, maybe a different color. Okay, choose a generic path from this torus to this point, and you start deforming this holomorphic curve. So the set of points on this curve that do lie on a holomorphic torus is open. And then you can use the closedness theorem to say that it's closed as long as you allow singular limits. Now, singular limits are problematic because they could be rigid, they might not move. But if you can show that the number of singular limits you can get is somehow not dense, if you can, for example, compute the Hausdorff dimension of the set of points that lie on singular limits and show that it's less than full Hausdorff dimension, then you can show that as long as you choose your path correctly, you can avoid all the possible singular limits and connect any 2 points. So so that's where the sort of technical argument comes in. And for that, if you get some sort of singular limit, so let's draw a singular limit like this. So the idea is to, so you can, the idea is you get singular limits from the compactness theory for J holomorphic curves, compactness theory. So this sort of Gromov-Sachs-Uhlenbeck theory. And then the idea is to compute the deformation, to understand the deformation theory for these singular limits. So understand the deformation theory. And the idea is to show that the space of deformations is always essentially is the right dimension. Essentially, you want to show that it's well, I mean, ideally, you'd like to show that it's 0-dimensional, which would imply that it's somehow rigid.
Yes. So you sort of think of the fibers as J holomorphic curves?
That's right, yeah.
Okay,
exactly.
thank you.
Yeah.
I guess you could have appealed to some geometric measure theory and their older theorems about limits of holomorphic cycles. I think that sort of strange in an integrable context to have to appeal to the theory of J holomorphic curves. I think it's older stuff, isn't it? But
yeah.
Works though. That's the
Maybe
important
it's
thing.
theorems of Harvey and Lawson on holomorphic cycles.
Yes, yes.
That's right.
I'm just sort of wondering about the volume growth of all of, so in the case when you're looking at, you have this very large class of Calabi-Yau metrics using the results of Hein in
Mhm.
different Bot-Chern cohomology classes.
Mhm.
Do they all have the same volume growth?
Yeah, they all grow like r to the 4/3 or something. So it's a weird fractional power of the radius.
But it's that's the same as you would get in the Tian-Yau. So
Exactly.
So
Yeah.
when you've done your hyperkähler rotation, you haven't changed the distance, you haven't changed volume, so it's got to have the same
Right.
volume growth.